Okay, well, hello everybody. Very glad to see you all interested in science and cocktails and music. And so the title of my talk is Certified Quantum Randomness. And basically this is what I'll walk you through. So I'll first talk about what is randomness, then a bit what is quantum mechanics. That's a tough one, and then maybe more tougher, what is non-locality and how one can use it to certify the existence of quantum randomness. But to start, let me go back to basically philosophy and how the idea of randomness came up. And it really came up from its opposite, which was determinism. And so this is Pierre-Simon de Laplace, and who studied probabilities, but he also knew the theory of Newton on the dynamics of Newton of planets. And he knew that in this theory, if you know all the positions of the planets at one moment and all their velocities, then you can extrapolate in the future and know all the future positions of the planets. And you could also do it in the past and know what were the past positions of all the planets. And so he extended this to, well, probably this holds for the whole universe, and that if you knew the present state of the whole universe to absolute precision, you could know all its future state and all its past state. And so this is a very nice idea. And here is a more humoristic vision of it. It's a little limerick, a traditional English poem. There once was a man who said, "Damn, it is born in upon me I am, an engine that moves in predestinate grooves. I'm not even a bus, I'm a tram." And, well, at least from the philosophical point of view, you can oppose to determinism the idea of free will, which is quite difficult to define. But maybe one way of expressing it is to say that it's the possibility to make choices free from constraints. It's not an extremely scientific concept. Determinism also comes up in other contexts. For instance, social determinism, the idea that your life is determined by, what the professions and the social standings of your parents and so on. Nehru, the founder of India, said that life is like a game of cards. The hand that is dealt to you is determinism, and the way you play it is free will. So determinism clearly and randomness have something to do with the way we live, how we see life around us. But it's also something which is very important in art. For instance, this is a painting by Jackson Pollock, a famous painter from the mid-20th century. And where you can see that there's a lot of randomness in this painting. I guess I find it quite appealing, but clearly it's not everything is thought out to 100%. In fact, here you see him dribbling paint on his canvas and trying to make, well, these pictures or drawings, sort of random drawings. Another interesting place where randomness comes up in art is in these two films, which maybe some of you, or at least the older people in the audience, may have seen. They got the César of the best film in 1994, Smoking and No Smoking. They're based on some plays by Alan Ayckbourn, and in these films what happens is that the initial situation is the same, and then somebody smokes a cigarette or doesn't smoke a cigarette. And depending on this, the whole future of the story changes. People get married, don't get married, have children, divorce, all kinds of things happen, depending on one incident which then has important consequences. And there's not only one incident like this, but there are many. I think the film has maybe something like 8 different endings, and the play has even more. And so it's a very nice film. I really liked it when I saw it at the time. And this aspect of randomness, smoking a cigarette, not smoking it, and then different things happen, is what in physics we call the butterfly effect, which is the idea which was put forward by people studying the atmosphere and the dynamics of the atmosphere in the 1960s by basically Lorentz, who had this image that you could have, small effects could sometimes be magnified into very big consequences. For instance, his picture was, I have a butterfly which flutters its wings someplace in the Amazon forest or doesn't flutter its wings, and depending on what the butterfly does, well, this can change the air currents and then change more and more air currents, and maybe a few weeks later you have a tornado, or you don't have a tornado someplace, I don't know, in the United States, say. So this is the sensitivity to small changes which can have big effects, but this is not really randomness. Random, because if you knew in Laplace's approach, deterministic vision, if you knew exactly all the air currents and the position of the butterfly, etc., well, you could know whether or not the tornado would appear. So to understand randomness, it's useful to go to applications of randomness. What is it used for? What is it useful for? It gives us a better understanding of what this is. And it plays an important role, for instance, in game theory. If some of you play poker, well, you know that to play poker well, you should use a random strategy. You should sometimes, pretend you've got stronger cards than you really have, bluff, sometimes not, but you can't do this systematically. If you always bluff, then people will call your bluff all the time and you'll just lose all your money very quickly. So you have to play in a random way, and it's this random strategy which is the best strategy to play some games like poker. And of course, poker is an example of many other situations which occur in the real life, where random strategies can be the best strategies when you've got opponents and you have to play against these opponents. As an interesting example, randomness also comes up in biology. And a very nice example is meiosis, which is the process in which the body makes sex cells, so the spermatozoids or the ova. And this is a little schematic of what happens. Here is a parent cell which has 2 chromosomes. Here, the example is with 2 chromosomes. We have many more. 2 from the father, here in blue, and 2 from the mother in red. And you're going to create the sex cells which just have 1 chromosome of each type. But the process is going to put a random piece of the father's chromosome and random pieces of the mother's chromosome into each of the ones in the sex cell. And in this way, when you have an offspring who combines this with a sex cell from the other parent, well, you have a random combination of the original genome of the father and mother. This is why your children don't look all the same. They share half of their genome between each other. And this is presumably a good strategy evolutionary strategy, so that there's some diversity in the population, and that if there's a good combination of genes, for instance, it can appear and be then successful. So this is the basics of sexual reproduction from the genetic point of view, and it uses this random strategy. Another nice example, again, it's a bit like a game. Like game theory is the immune system, the way our body fights invaders. And there are different ways the body does this, but one of the most important uses a random strategy. The body makes these special molecules called immunoglobulins, which have this structure which you see here. There's a fixed tail and then some sort of antennas which are made at random. And then once such a molecule is made, the body tests whether it's going to, these antennas are going to bind to your own molecules in your body. If yes, it's not good because that would give an autoimmune reaction, but if not, then this molecule is sent into the body to see if there's an invader, a bacteria, a virus, which it would recognize. And this is a kind of random strategy which clearly seems to be good to be unsure that maybe one person will not recognize the virus, but somebody else will make the right molecule, the right immunoglobulin, and be able to fight off the invader. So these are sort of examples from game theory, here applied in biology and evolution. Randomness is also very important in simulations of physical phenomena, what we call Monte Carlo simulations. And the basic idea is that there are many problems in science and engineering which are so complicated that we just can't solve them exactly, what we do is we do a simulation taking into account different possibilities of random processes, of noise which can affect the system. For instance, this is an example of some kind of stock or which is its value is growing, and is growing in a random way, and you simulate the random events which can change its value as time goes on. And this can be applied, is applied sometimes to extremely complicated problems where we don't have other techniques to do it. But the place where randomness is the most clear what it is and what it's useful for is in cryptography. And randomness is really essential in cryptography. It's at the basis of all the security of the internet, of banking transactions. All of cryptography relies on random numbers. Just, for instance, your PIN code for your credit card, well, it should be a random number. If it's your birthday, it's not a good idea because somebody who steals your bank card could guess what is the PIN code and use it. If it's if it's the birthday of your wife, again, not a good idea. So it should be a number which, if somebody steals the card, he can't guess what it is. And this is really what you mean by a random number, something which you cannot guess what it should be. So the random numbers should be unpredictable for an adversary in the cryptographic setting, somebody who wants to use your PIN code, somebody who wants to eavesdrop on your conversation on the internet. Well, this person should not be able to do it because the random numbers which are used are unpredictable, unknown to him, and he would have to try all of them. And you can extend this, for instance, even if somebody knows some of the random numbers, he should not be able to guess others. For instance, if you know the PIN code, somebody knows the PIN code of your credit card, he shouldn't be able to guess the PIN code of your wife's credit card. So, and this gives a good understanding of what we mean by randomness. Really, it's something which is not predictable by an adversary, by somebody who would like to try to know what it is. And if you have a bad source of randomness in your cryptographic system, this makes for easy cryptanalysis. It simplifies cracking the system. The most famous example of this is the Enigma Machine, which was used by the Germans during the Second World War, and they had devised this cryptographic machine. You see, it's got a keyboard here, and then there's a whole set of settings, rotors you can put, plugs you can change, and this machine was used to code messages by the Germans during the Second World War at the highest level. And the Allies were able to crack this system, but they were really only able to crack it because the Germans weren't using the randomness, the random settings, the positions of the rotors, of the plugs, as well as they could. They were using the same ones, they were not changing them very much, and this made it much easier to figure out, the next day or the next week what was the code being used that day. And if the Germans had been using the machine to its full capability, really using the maximum amount of randomness in its settings, well, it would have been another story, and it could have had some quite huge historical implications. So, well, this leads us to, well, how do you generate random numbers? And how do you certify that the numbers that you generate are really random, that they're unpredictable? And this is not easy. This is a little cartoon from Dilbert. This little troll presents over here. We have our random number generator. 9, 9, 9, 9, 9, 9. Goes the random number generator. Are you sure that's random? That's the problem with randomness. You can never be sure. and it's true. Maybe this is just, one in something like a million chance that it produced 6 9s in a row, and then the rest is going to be other numbers. And maybe there's a defect in this device, and it only outputs 9s. And, well, yeah, it's not easy. It's not an easy problem. It's a problem on which scientists have worked a lot, as once they understood that random numbers were really important for applications. So today, what are the solutions we use to generate random numbers? Well, the first one and the most easy and the most often used are what are called pseudo-random number generators. And these are digital implementations of the butterfly effect. So they're little pieces of code which take some initial value and then generate a very long string of numbers which depend in this very sensitive way on the first initial values which are inputted into this piece of code. And these produce good sequences of numbers which are quite close to random. But of course, if you knew what is the little piece of code used, well, then you could predict all the future sequence based on this very small length of code. I mean, these codes can be extremely short, and so this is not perfect. It's very practical because it's digital. You can use it very simply. But so this is one technique. There are also hardware random number generators which use physical effects to generate random numbers, and one of them is basically analog implementations of the butterfly effect. And another approach is to use randomness coming from quantum effects, from quantum mechanics. And so that brings me to the second part of my talk, where I'm going to discuss a little bit what is quantum mechanics. And, well, this is a very complicated topic. It takes a very long time to teach our students at the university what it is and how to use it. But basically what it is, it's the theory of matter at the microscopic scale. It's the theory of matter at the scale of individual atoms, of individual photons, individual particles of light. For instance, it will describe what happens where an atom, symbolized here with a nucleus and some electrons, absorbs a particle of light, a photon, and the electron goes to an excited state. This kind of process is described by quantum mechanics. Quantum mechanics was sort of started to be guessed at in 1900. This is the sort of founding paper by Planck, and then gradually evolved until around 1925, 1926, just almost 100 years ago. The theory was really formulated, and then basically after the Second World War, there started to be a very large number of applications, and well, this continues today. Planck, he was trying to understand what is the properties of light emitted by hot bodies. If here you have some very hot lava, and depending on its temperature, the light emitted is either yellow or red or very dark blue or black. When it's black, it's emitting infrared radiation, which we don't see, but which you could measure with another device. And he tried to formulate what was happening in this process, and in doing that he introduced a new constant of nature, which we now call Planck's constant. And quantum mechanics is an extremely powerful theory and has really completely revolutionized our world. To give you some ideas of applications, well, if you want to understand how a metal conducts electricity, like a copper wire, well, you really need quantum mechanics to understand this, but okay, it's not so complicated. On the other hand, you also have materials like glass, which are isolators, which don't conduct electricity. Okay, these materials are not too complicated to understand, but in between the two, there's a class of materials which we call semiconductors, which just barely conduct electricity. And these materials, how they conduct electricity depends very strongly on temperature, very strongly on dopants. If you put some impurities in the material, the way it conducts electricity changes completely. And to understand semiconductors, you really need this theory of quantum mechanics, how they conduct electricity. And this turned out to be extremely powerful and gave rise to the transistor, which is the basic element we now use in all our integrated circuits, in all our computers. And it really came from understanding how electricity is conducted, how the electrons move in these materials called semiconductors. Another example of application of quantum mechanics, well, let's go back to, we said Planck used this theory, introduced this idea to try to understand the emission of light by matter. Of course, there are many different ways that matter can emit light, and you really need quantum mechanics to understand these different mechanisms. You also need quantum mechanics to understand how light is detected, how the retina works, how a photographic film works, how photosynthesis works. All these are quantum phenomena which happen at the level of absorption of a photon by some molecules. And when you put together these two knowledge fields of, well, ideas, you can make a completely new kind of light source, which is the laser, which uses really how matter emits light, how it absorbs light, and these lasers have become extremely important. Well, for instance, they can be used in eye surgery, but the most important, I guess, is their use in telecommunications and in the internet, which would just not work with the speeds we know without using lasers. And their lasers are now every place, like in my laser pointer. And there are many other applications, for instance, the atomic clocks, which are used in the global positioning system for your GPS. They're atomic clocks, which are really based on quantum mechanics, on the satellites which send us these signals, in, for instance, nuclear magnetic resonance, which is used, for instance, in imaging in hospitals. You really need quantum mechanics to understand how these systems work. So this has been one of the greatest success stories of science, where really curiosity-driven science at the beginning of the 20th century has completely transformed our world a few decades later. It's really, as I said, one of the greatest success stories of science. But what's going to interest us here is the connection between randomness and quantum mechanics. This connection was made just after the theory was formulated by Heisenberg and Schrödinger, by Born, basically the same year. And what Max Born did in his seminal paper was that he understood that the theory of quantum mechanics, which Schrödinger and Heisenberg had just developed, could apply to the situation where you have a particle, say an electron, which scatters off an atom. These are experiments which people had been doing since the 19th century, scattering experiments where you send some particles and some matter, you see where they go, and you try to understand the properties of the particles you send, the properties of the matter. This was, for instance, how it was discovered that atoms have nuclei. But Max Born realized that he could apply the theory of quantum mechanics to these kind of experiments. And when he did this, he found that the theory was describing simultaneously all the possible outcomes of the experiment. It wasn't saying this electron is going to go in this direction. It was saying this electron is going in all directions simultaneously. And so he concluded, the conclusion he reached was that there's only one interpretation which is possible. Phi, this is the quantum mechanical wave function, the quantity given by the theory, must give the probability for the electron arriving from the z direction to be scattered into the direction given by the angles alpha, beta, gamma. If the theory is really giving you all the possible outcomes of the experiment, then what it must be giving you is the probabilities for these different outcomes. And this result is now known as the Born rule, Born interpretation of quantum mechanics, how you use the theory to predict probabilities. And then he concludes his paper with a very interesting discussion where he says, well, the problem of determinism comes up here. Because should there be some inner property of the atom or the electron which conditions a definite outcome for the collision? That is, it may be things are in fact determined beforehand, and where the electron is going to go is determined by something else which isn't in this quantum theory. And then he says, well, I myself am inclined to give up determinism in the world of atoms, but that is a philosophical question for which physical arguments alone are not decisive. So what he means is that you could have some kind of, the electron, for instance, could carry some internal information which tells it, well, this time when you reach the atom, you're going to scatter it at 30 degrees. And the quantum theory is just giving the probabilities that it's going to scatter in different directions, but in fact there could be some internal information which is giving the electron and the atom the information, the instructions on what they should do. Well, and we'll come back to this all along the next parts of the talk. Well, when Born formulated this probabilistic interpretation of quantum mechanics, one of the people who reacted straight away was Albert Einstein. He wrote a letter to Max Born. You see, all this is the same year. In it, he had this famous quote that God does not play dice. What you're saying shouldn't make sense. It shouldn't be like that. Nowadays, you can buy systems which do this kind of experiment to generate random numbers. So you can have a little source, for instance, of photons, which are separated into two beams, which go to two detectors, and depending on which detector clicks, you have, you say the outcome is a 1 or a 0. And these kind of devices, as I said, you can buy them. They fit into the palm of your hand in little cards you could add to a computer. So this is a kind of experiment which is, in fact, nowadays very easy to do. But this is what I would call an uncertified random number generator, because whether or not the numbers coming out of this device are random really depends on whether you trust what's inside the device, that it's doing this operation. But if you don't trust it, maybe the device is doing something completely different. Maybe it's got a little chip and it's just reading the numbers on the chip, and then, well, the numbers coming out are not unpredictable. They're not random. So, can we do better? We can, first, can we answer the question whether quantum processes are really random? And can we certify that the outcomes of a random number generator are really unpredictable? And to answer these questions, we need to go to a new kind of concept, a new kind of experiment, which goes under the name of quantum non-locality. So this kind of experiment was first, its origin, sort of its ancestor, was formulated by Einstein, Podolsky and Rosen in 1935. And they imagined an experiment which works like this. They had a source which produced two particles, one which goes on the left to Alice, and one which goes on the right to Bob. And Alice has a detector which receives the particle and which registers an outcome. It lights up a red light or it lights up a green light. And same thing for Bob's detector. Either it lights up red or it lights up green. And the device is, you can build a device like this with a quantum source of particles, which is such that it will always, the lights will always be both red, as in this example, or both green, as in this example. And this experiment, well, you can do nowadays without too much difficulty. But what does this experiment tell us about randomness? Well, it doesn't really answer the question, because we can imagine that the particle going to Alice, for instance, has its internal instructions would tell it light up the green light. And Bob's particle has some internal instructions which would tell it to light up the green light. And this would allow them to light up both green lights, or if both particles had the instructions to light up the red light, you could have red-red or green-green with equal probability depending on how you choose these internal instructions. So this experiment doesn't allow us to answer these questions, but it was the starting point for another experiment which was conceived by John Bell in 1964, so 30 years later. These were, really difficult questions to understand how to formulate them and what to do. And John Bell just made a little twist to this experiment. He added a way to change the internal workings of the measurement device. Here I've symbolized this with a little lever which can be in the up or down position, and same thing on Bob's side. So depending on whether the lever is up or down, the device will work differently, but once the particle enters, it'll light up either the red or the green light. And what you would like these devices to work in the following way, is that if at least one of the levers is in the up position, then both lights should either be green or both red. For instance, here Alice's lever is up, Bob's is down, so the two colors should be the same, and indeed they're both red. But if both the levers are in the down position, then you want the colors to light up with opposite, the colors to be opposite, green-red or red-green. Now, how would you try to do this if you had these hidden internal instructions? Well, these instructions now have to be a bit more complicated because they have to take into account what is the possible positions of the lever. So, for instance, Alice's particle's internal instructions should be something like saying, if the lever is up, light up the red light. If the lever is down, light up the green light. And same thing on Bob's side, for instance, here, whatever the position of the lever, always light up the red light. We don't know exactly what would be the internal mechanisms of all the device, but we suppose that there's some kind of instruction which determines what light would light up. And if we do this, and we want that these correlations are obeyed, if at least one of the levers is up, both lights are the same color. If both are down, then the colors are opposite. Then we can only reproduce this 75% of the time, 3/4 of the time. For instance, in this example, you see what happens if both levers are up, then indeed we have red and red. If Alice's is up and Bob's is down, we also have red and red. That's good. If Alice's lever is down and Bob's up, we have green and red. That's not what we want. If Alice's lever is down and Bob's down, we have green and red, which is what we want. So one of the 4 cases won't work. And it's easy just to enumerate all these possibilities and to see that, well, you can do it 3/4 of the time correct, but you can't get it more. What happens if you do this with a quantum system? You do a quantum experiment. I'll describe some of these experiments in a little bit more detail later. So you have to produce a quantum state of particles which are entangled. This is sort of our mathematical way of writing this. And you want these correlations to appear. And if you devise how the measurements work in the correct way, you can do better than 3/4 of the time. You can reach, in fact, 85% of the time correct. And that's really quite remarkable. We had this in a deterministic model, in a model where we could know beforehand what would happen in the devices. The success rate was maximum 75%. And if we do the theory, or we do experiments, and many experiments now have been done on this, you can get a success rate of up to 85%. So even more. So something must be wrong in the deterministic model. Look, this is really why quantum mechanics, you can use these experiments to show that quantum mechanics must be really random. The outcomes of these measurements, of these experiments, must be random, must be unpredictable. because they're in contradiction with the deterministic models. Here's an example of an experiment, one of the most early ones and most famous ones done on this by Alain Aspect in Paris. And so this is the schematic of his experiment, where he has a source which produces two photons, called nu1 and nu2, and they reach here a kind of a switch, and either the switch sends the photon straight, or it sends it towards the bottom here, and then if it goes straight, there's a certain one particular measurement which is done on the photon. If it goes in this path, there's another measurement which is done on the photon. So this is sending the photon straight or down, corresponds to the position of the switch, up or down, and then you do a measurement here or a measurement there, and you register the outcomes. Same thing for the photon on the other side. There's a switch which sends it straight, or which sends it to this measuring device or that measuring device, and the switch behaves like the lever in these experiments. And this experiment indeed gave results which were in agreement with quantum theory and not in agreement with the deterministic models. Now, this experiment and many others have been analyzed in great detail to try to understand what are they really showing. And people came up with what are called loopholes in these experiments, which would be ways in which you could still explain what's happening with a deterministic theory. And here are three of these loopholes. One is the randomness loophole, which is that the choices of the lever position of what is the setting of the measurement must be random, must be unpredictable to the particle, because if the particle knows that the lever is going to be in the up position, then it can, its task is much easier, and then it could in fact just get 100% success rate. There's another loophole which is called the locality loophole, which is that it shouldn't be possible for the system to communicate instantaneously from one device to the other. Otherwise, again, you can arrive here, say, oh, the lever is up and I've lit up the red light, now you do what you need so that the correlations are correct. And again, you can reach 100% if you could have some kind of communication between the devices. And the last one is more technical, it's called the detection loophole, which is that, in fact, in many experiments, such as this one, a lot of the times the detectors didn't register the photons. They didn't click, so it's as if the particle arrives and no light lights up, neither the red nor the green. This is sort of a technical problem, but if it's like that, again, you can, if too often the lights don't light up, you can model what's happening with a deterministic model. So people have worked a lot to try to improve these experiments and really get to the point where you couldn't explain what was happening with a deterministic model by exploiting one of these loopholes. And this is one of the first, maybe the first experiment which really closed all these loopholes, which was done in Delft in 2015, so not very long ago. And they created an entangled quantum state between two defects in two diamonds located on two parts of places in the campus of the university, separated by a bit more than a kilometer, and then they could do measurements on these two diamonds and find that the results couldn't be explained by these deterministic models, and the loopholes which I just mentioned were all closed, were all you couldn't be exploited by a deterministic model. So this, of course, has implications for our understanding of randomness, because if you do this experiment and if you see the correlations, the ones you want, as explained here, if at least one of the levers is up, you have the same colors lighting up. If both are down, you have opposite ones. If this is correct, happens more than 75% of the time. And if you've made your experiment so that instantaneous communication between the devices is not possible, if the measurement settings are not known beforehand, if you don't have this detection loophole, then the results must be random. That is, what light, whether it's a red or green light, must be random because it can be explained by a deterministic model. That is, it's undetermined until the moment of the measurement. It's completely impossible. Nature doesn't make it possible for you to know beforehand what would happen. The outcome is necessarily unpredictable. And so this gives rise, it's really a fascinating result, but it also could be used to create a new way of generating random numbers, because we know that these experiments produce new outcomes which are unpredictable, which don't exist until the moment you do the experiment. And this randomness which is produced is certified by the fact that statistics of the measurement devices. That is, by the fact that these correlations are obeyed, say, 85% of the time. And you don't need to model what's happening inside your devices, contrary to the simple device I showed you before. It's really just what the statistics of the measurement outcomes which are telling you that the device is working correctly and is producing new randomness. So, this is a nice idea, and it was then, it has been implemented experimentally. This is the first experiment which tried to use a non-locality experiment like this to generate random numbers. It was in 2010, and it was a very slow experiment. It used the two systems which were measured were two ytterbium ions in two traps in vacuum here and there. And they were then untangled and then measured, and it was an extremely slow experiment. It took a month to generate something like 40 new random bits. Very slow. But, of course, things improve, and this is an experiment which was done more recently in 2018, where you have this now used as photons, which are produced by a source, so very much like the experiment of Alain Aspect, but only 35 years later, and so with much improved technology, a source which produces two photons, one goes to Alice, the other goes to Bob, and then here they're measured, so this is a schematic of what happens at Alice's side. You've got the photon coming from the source, here it goes through some optical elements, and one of these optical elements changes the polarization of the photon, and then it's detected here, and whether or not it's detected is registered. And you also have here this random number generator, RNG, which is used to determine what is going to be the measurement done on the photon. This is the setting of the lever which is chosen here. And this experiment still wasn't extremely fast, but in a few minutes it could produce around 1,000 new random bits. So we see these experiments can produce randomness. How much randomness can they produce? And in fact, there's a nice way of bootstrapping these systems, where you take your initial randomness, which determines the settings of the measurement device, the positions of the levers, and what lights light up creates new randomness. And this randomness is, the fact that new randomness is produced is certified by the way the correlations between the positions of the levers and what lights light up. And then you can use this new randomness to choose the settings of the measurement devices in the next run. And you can produce even more randomness. And if you optimize this process, at each step you can really just boost the amount of randomness which is produced. And you can, in fact, from just a small, finite initial random seed used to initiate the positions of the levers, you can produce an indefinite amount of new randomness at the end. So this idea of using these non-locality experiments to certify the generation of randomness can also be applied to other applications, like certifying that a quantum cryptography system works well, or certifying that quantum computers work well. But, I won't go into these possible applications. These are much harder to do experimentally, and there have not been any experiments in this direction. And so I'll start concluding my talk here with a discussion a bit about what we have learned in in this investigation. And, well, we've learned that the outcomes of quantum experiments are random. They're unpredictable. These outcomes do not exist until you carry out the measurement. And you can demonstrate that this is the case using these non-locality experiments, which have been gradually improved over the decades. And yeah, sort of just the last, less than the last few years have really got to the point where they are close all these loopholes, are really doing what you would like the experiments to do. And this, of course, answers Born's question, whether quantum mechanics is random or not. He said this is something which science can answer, but in fact, using these experiments, we now know that indeed the deterministic model doesn't work, and you really have the outcomes of quantum experiments, quantum experiments are going to be random. And as I said, quantum mechanics has many applications, and there are possibly some new applications in generating random numbers. Of course, this is much less, going to be much less important than applications like these, but these are some interesting developments. And, well, to conclude, we can go back to the philosophical questions, which we, discussed at the beginning of the talk. And, I started all this talk with the determinism of Laplace, who, thought that everything was completely determined. If you knew the present conditions of the universe, you could know all its future. And obviously, this can be true because we've got this quantum randomness. And so, in fact, what must be happening is that at the microscopic scale, we have random, unpredictable events which are taking place continuously, whether a photon is absorbed by an atom or not, whether a radioactive atom decays or not. All these events are unpredictable and are taking place continuously. And then, presumably, this is why I say you should take this with a grain of salt, because this is, I'm trying to extend this. These random events are get amplified into macroscopic consequences, like the butterfly effect I talked about before. So you may have some random events, random absorption or not of light by a molecule, by an atom, and then this could give rise to some other effects, say in the atmosphere, and finally could give rise or not to a tornado someplace. Or to give you another example, you know that our genetic code is encoded in DNA, and this DNA gets mutated, and this is how living beings evolve. And then there's a natural selection. If the mutation is advantageous, well, it may be selected. But these mutations arise because of effects at the, it's really chemistry, it's an individual molecule which can get damaged. And this is what happens. The molecule gets damaged, for instance, by an ultraviolet photon, by a cosmic ray, by something. And then when the body tries to, the mechanism inside the cell try to repair this damage, they can in fact introduce an error. And then this error could be given onto your offsprings. And, well, these random events, which, because they're at the chemical level, should be described quantum mechanically and are therefore random, could give rise to different final paths in evolution. For instance, this horse getting longer ears, or getting horns, or no ears. And of course, well, it will only be selected if this was advantageous from the point of view, of evolution. So, with this, that brings me to the end of my talk. And, well, thank you for your attention.